Our next section is going to cover a type of reaction called a redox reaction. And some of the ones we've already done are technically also underneath the redox category, but this is going to specifically explain what those reactions are. So we've had four types of chemical reactions. We've had synthesis reactions, we've had combustion reactions, decomposition reactions, and replacement reactions. There's other ways to quantify them when it comes to redox. Now, redox is going to deal with transferring of electrons, so the charges on things are going to change. So another way to classify them is oxidation reduction reactions, or for short, redox, okay, is what we call these. This is any reaction in which electrons are transferred from one substance to another. So here's just kind of a picture example. This is combusting magnesium. If you've never seen magnesium burn, it burns very brightly and very hot. These are used in the strobe lights on the 4th of July. That's how bright this stuff is, if you know what those are. Magnesium metal by itself, right, is neutral, and oxygen gas by itself is neutral. But when you burn it, it produces magnesium oxide, which is an ionic compound. And over here on the product side, you have magnesium that now has a +2 charge and an oxide that now has a -2 charge. Well, what's going on, okay, is during this combustion of magnesium, you have electrons moving. You have electrons moving from magnesium atoms to oxygen atoms. You've got 2 electrons leaving a magnesium and arriving on a single oxygen, okay, is what's going on here. So this is a redox reaction. The charge on things change. And on the left side here, both of these things have a charge of 0. And on the right side, magnesium's +2 and oxygen's now -2. So the electrons are moving. And so what redox and what this section is going to cover is what's really going on here with these electrons moving around. Okay, so let's start with oxidation. That is the complete or partial loss of electrons. We're putting things in terms of electrons. So what this is going to look like, these are called half reactions, is what you're going to see here. Okay, is you're going to see some either element or ion, and then on the other side you will see it gaining charge while losing an electron. Okay, that's what this is going to look like. It's losing an electron. Electrons coming off of it, so it'll be on the product side. So to occur, the electron then must be accepted by another reactant. This doesn't just happen for fun. This immediately goes somewhere. So this happens in conjunction with a reduction reaction, okay, reduction half reaction. So it does not happen by itself in a vacuum. So the complete or partial gain of electrons, okay, is reduction. So now you'll see it on the reactant side. So here, for instance, you'll see chlorine picking up 2 electrons. Each chlorine picks up 1, and it becomes 2 chloride ions. Okay, oxidation and reduction are complementary processes. So whenever one occurs, oxidation occurs, then reduction occurs in conjunction with it. Trying to remember which is which. There's a couple of famous ones for this. We've got Leo and Gur. And that's what's written down here. Leo the lion says Gur. I know lions don't really say Gur, but it's a way to remember this, and that is that losing electrons is oxidation. So we fill that in here for a sec. Losing electrons is oxidation. And the other one here then is going to be gaining electrons is reduction. Okay, so Leo says Gur. So losing electrons is oxidation, gaining electrons is reduction. Another one that you might see elsewhere is oil rig, and that is oxidation is losing, reduction is gaining. So either one of those, whatever it takes for you to commit this to memory, remember which one is oxidation and which one is reduction, right? Losing electrons, gaining electrons. Remember which one is which, because it will show up on the final at the end of the semester. Okay, so as far as electrons moving around, they're going to have an effect on the charge, or what we're going to call now the oxidation number of something. Okay, that's the number assigned to an atom or ion to indicate its degree of oxidation or reduction. So in this example here, right, we've got potassium atoms with diatomic chlorine yielding to potassium chloride. Okay, 2 units of potassium chloride. Potassium loses 1 electron and has an oxidation number of +1, so it goes from 0 on this side as an element to +1 over here. And each chlorine is going to gain 1 electron, so it starts at 0 and becomes -1. Okay, we'll go through how to do all of this specifically, but the oxidation numbers are basically what we want to think of as the charge of something, and there's some basic rules that we can use to help us remember that. In addition to Leo and Gur, here are a couple of other helpful things to remember. When something is getting reduced, when an atom or ion is reduced, the oxidation number goes down, right? But remember, this is gaining electrons, okay? So remember, electrons have a -1 charge. If you're gaining a -1 charge, your oxidation number is going to go down. It's a little, counterintuitive at first, okay? And if something is getting oxidized, right? Remember, oxidation is losing electrons. Okay, you're losing a -1 charge. Your oxidation number goes up, right? So if you're, doing the algebra of it, minus -1 is really adding things. Okay, so you have to keep in mind those electrons have a -1 charge, and that affects which way the oxidation number goes. But remember Leo and Gur, and remember what happens to the oxidation numbers. Okay, using that same example we were before just a minute ago, it's also helpful to know these terms, oxidizing agent and reducing agent. And I know that this is going to sound really weird as to why we do it, but we'll explain here in just a moment. So the oxidizing agent is the substance that oxidizes another substance by accepting its electron. It's the thing that gets reduced. I know, it's kind of weird, right? The oxidizing agent is the thing that gets reduced, and the reducing agent then is going to be the thing that gets oxidized. It's a little strange, right? Maybe perhaps with this naming here, but the reason we call it that is it allows the other thing, okay, if it's an oxidizing agent, it gets reduced, but it allows something else to oxidize. And if you pick up, chemicals at the hardware store, if they are in any sort of redox type of chemistry, it'll say, like, warning, strong oxidizing agent, or warning, strong reducing agent on the side of it. Okay, so that's what the terminology is. That's actually how it's written here. Okay, so in this reaction, potassium gets oxidized. It goes from 0 to +1. It loses 1 electron. Okay, it will also be the reducing agent. Okay, this elemental potassium would also be called the reducing agent. So it gets oxidized. It's also called the reducing agent. The Cl2, okay, this should say is reduced. Cross that off. Okay, is reduced in this reaction, right? It goes from 0 to -1. It's the same one as the previous slide. It is the oxidizing agent. Okay, so let's run through an example here. If something has a charge, that will be its oxidation number, so that's very helpful. And so in this first example that we'll go through, elemental aluminum, does not have a charge, so it has an oxidation number of 0. This iron here has a +3 charge. This oxygen has a -2 charge. And then on the right side, the iron now has a charge of 0 as an element. The aluminum has a +3 charge, and the oxygen is still -2. So let's look and see what changed. We saw that the aluminum goes from 0 to +3, and we see that change the color here, the iron goes from +3 to 0. Okay, let's think about what happened. If the oxidation number goes up, okay, that thing got oxidized. All right, and if the oxidation number goes down, it got reduced. So aluminum here goes from 0 to +3. It gets oxidized. It lost electrons, right? Leo, yeah? Okay, loses electrons. The iron got reduced, right? It gained electrons. Okay, its oxidation number went down. So which substance is being reduced? Well, that is let's be careful here, because is it this one or this one? Well, over here on the right side, it's already been reduced. So we want to say the one on the left side here. So that is the Fe +3. Which substance is being oxidized? Well, that will be the aluminum here. Okay, so that's the Al. Not the Al +3, because that's already been oxidized. Which one's the oxidizing agent? Well, that's the thing getting reduced, right? So that is the, oops, change that back to the pen. That is the Fe plus 3, and the reducing agent is the thing being oxidized, so that would be the aluminum. Okay, here's a reaction for you to look at. Identify what's going on, whether something is gaining or losing electrons, and answer the questions underneath there. Okay, so let's say that it's not just listed an oxidation number as a charge. How could you figure it out? Well, here are some basic rules, right? Anything that is an uncombined element is going to have an oxidation number of 0. So, anything without a charge. So sodium by itself, elemental, is going to be 0. Oxygen, which is O2, right? It's diatomic, but it's still 0. Chlorine, which is Cl2, diatomic, still 0. Okay, so that's the first one here. Anything that's an element without any charge or anything to it is going to have an oxidation number of 0. The oxidation number of monatomic ions is just whatever the charge is. That's very simple. So if this is +2, then it's +2. If it's -1, it's -1. We're not going to worry about rule number 3. That's not going to apply to us, at least in this class. Rule number 4, fluorine is always going to be -1. That's going to be fairly straightforward. Rule 5, oxygen is typically going to be -2. The only time it's not is if it's a peroxide, and frankly, we're not going to encounter those often enough for you to think about them, and if they are, I will tell you that you're being given a peroxide. Generally speaking, oxygen, when it's in a compound, let's treat it as -2. Okay, that's going to be the easiest way for us to remember that. Okay, so that's kind of important. So big ones to take away here: elements by themselves are always 0. Okay, things that are monatomic ions, it's whatever the charge is, and oxygen is -2. Okay, the oxidation number of hydrogen in most compounds is +1. All right, I want us to think of it like this. Don't worry about trying to remember this hydride rule. That's very rare. We're not going to see that. It's pretty advanced level chemistry stuff. We're not going to touch on that in a general high school class. Sodium hydride is not something that we keep on hand. Okay, so if you see hydrogen in compounds, it's going to be +1. Okay, I'll write that over here. Okay, in compound, right? By itself is 0, right? If it's H2 is 0. Let's see. The oxidation numbers of group 1A and 2A metals and alumina are positive and equal to their number of valence electrons. That's fairly straightforward. 1A metals are +1, 2A metals are +2, aluminum's +3. If you start getting things in compounds, the total of all the oxidation numbers has to add up to 0. And if it's not a compound, it's, let's say, a polyatomic ion, okay, like this sulfite ion down here, then it's got to add up to whatever the charge is, in this case, to be -2. Okay, so let's try one of these for practice. What is the oxidation state of chlorine in KClO3? So, rule 7 will tell us that everything, since it's a compound here, must add up to 0, right? Must add to 0, okay? Potassium is a 1A metal. 1A metals and compounds are going to be +1. Rule 5, oxygen in compounds is always -2. Okay, we're not going to see a peroxide or some sort of oxygen with fluorine. And so let's see what's going to happen here. So we've got, KClO3. Potassium is +1. There's one of them, right? Chlorines, we'll call that X since we're solving for it. Plus, okay, we have 3 oxygens, and each one is -2. And they have to sum up to a total of 0. Well, now you have 1 plus X minus 6 equals 0. We have X minus 5 equals 0. So X, the oxidation state of chlorine here, is +5. And that might be a little surprising because chlorine by itself as chloride has an oxidation number of -1. But we're going to see a lot of these halogens can have maybe some surprising oxidation numbers. Okay, here are 3 for you to try. Determine the oxidation state of the one that is underlined. And be careful with, I should probably underline the last one here. Let's do the chromium. Be careful with this, especially this last one. Instead of equaling 0, it should equal the charge of -2, and there's 2 of them. So whatever value you get, it's per the individual atom, not like both of them together. So you want to find the individual one.